Hello, good day have everyone, students and research. My name is Luis Ángel Magaña Gallegos, and today I come to present my research work called Synthesis and Characterization of Titanium Dioxide Doped from Hypodermic Needle for Photocatalytic Applications in the Degradation of Acetaminophen. In this study, we doped titanium dioxide using hypodermic needle as a doping method source in a concentration of 0.2, 0.5, and 1%. We know that titanium dioxide is one of the most used semiconductors in photocatalysis because of its photocatalytic properties. However, by itself it has some problems, like it only works under UV light and has a band gap of 3.2 eV, which makes easy for electron-hole recombinations. That's why many strategies are studied to improve the physicochemical properties of titanium dioxide, like the doped. So the main objectives of this work was to improve the photocatalytic activity of TiO₂ using a metal waste like hypodermic needles as a doping precursors to remove organic pollutions using as a model of contamination acetaminophen. The objectives of this work are to enhance the photocatalytic activity of TiO₂ using a metal waste as a doping precursors, to perform the structural, optical, and characterizations using UV-Vis DRS, XRD, and textural analysis to study their effects, to evaluate the degradation efficiency of acetaminophen under simulated solar irradiation. The synthesis that we use a Soljet method, but first we did acid digestion with 1 milliliter of chloric acid and 7 milliliters of water. As you can see in the figure 1, we increased the temperature to activate the acid as an oxidant and fully digest the needle. This was called solution A. In the figure 2, while the acid digestion just happened, we mixed 13 milliliters of titanium isopropoxide with 120 milliliters of isopropanol and keep stirring it. This was solution B. When the needles was fully digested, solution A was adapted drop by drop to solution B. A aerogel formed as was left again for 24 hours, and after of 24 hours the aerogel was transferred to rotavapor to remove solvents and formed granules, which were later ground and calcined for 4 hours and 50 degrees Celsius. The results, we have H points. We can see the section 4.1 DRX shows anatase phase signals. Crystal size decrease with doping increases. Non-doping TiO₂ has 18.41 nanometers and Ta 1% has 16.04, shows a crystal contraction. Also in the graphic we see shift 25.3 degrees in the 2 theta angle, confirming the reduction in the crystal size. Section 4.2, we see type 4 isotherms typical of mesoporous materials with a form mono and multi-cappas. Hysteresis circle is a H1 by EU pack, typical of open cylindrical pores. The range is 2 to 5 nanometers, favoring the molecular diffusions. Titanium has 50.30 squares per grams. The surface area, porous sites, we have 69.60 Armstrongs, total pore volume of 0.051 centimeters cubed per grams. And after doping, all the parameters increases. For example, Ta1% has a pore size of 91.45 angstroms and pore volume of 0.0945 centimeters cubic per grams, and obtained more than no doping titanium dioxide. In the section 4.3, dope samples no absorbs invisible regions. Non-doped titanium dioxide only in UV. This is because have a bandgap of 3.2 eV and Ta1% has a bandgap of 2.88 eV with a metallic band gaps. We can see these band gaps blue in the tau graphic in the graphic, meaning less electron hole recombinations. Section 4.4 photoluminescence spectra show recombination dope. The titanium dioxide shows a lower recombination rate. Ta1% has a lower intensity, which is good. Section 4.5 XPS table shows elements interacting with oxygen. In the case of Ta1%, this causes energy level shifting, confirming a metal dope in gradations. Section 4.6 Ta1% catalysis has a best degradation versus photolysis and no-doped TiO₂. This means multi-doping from nils improves the photocatalytic activities, tends to better light absorption and charge separations. Section 4.7 scavenger tests use ADTA for holes, benzoquinone superoxide radicals, silver nitrate for electrons, and butanol for hydroxyl radicals. In the graphic, we can see that ADTA and benzoquinone reduce activity, so holes and hydroxide radicals main shippings. Section 5.8 real cycles T1% was reused 5 times. After H once centrifuged washed with ethanol, dried for 4 hours and 70 degrees Celsius, low material loss, showing instability. Conclusions: doping titanium dioxide with a metal waste from hypodermic needles improves its photocatalytic performance, especially in the degradation of acetaminophen under simulated solar light. The structural, optical, and textural characterizations confirm this improves. The catalysis shows high efficiency, stability, and reusability, making it a promising material for environment remediations. Thank you.